Hello. In this video, we're going to look very briefly at what or how we can work with improper integrals. So there are two main types of improper integrals. Either one results in an area or a region that is unbounded, if we consider the area definition for a definite integral. So one situation can occur if one or both of the bounds is at an asymptote. So a vertical asymptote is occurring here when I have, for example, the integral from 0 to 1 of the curve 1 over x squared. So that would represent sort of this, if I'm thinking of a region on this graph, it would represent the region that is bounded on the left by the vertical asymptote at x equals 0. So this area that I'm doing in yellow here, and that is an unbounded region, but it may still result in a finite area. So this is something that does occasionally happen with these improper integrals, is that we can have an unbounded area that actually does have a finite area. And in order to figure out if it does or doesn't, we have to deal with limits. So what I do is I kind of go about this the usual way. I'm going to find an antiderivative of 1 over x squared. So 1 over x squared is just x to the negative 2, so I can just use my power rule. So the antiderivative of this is going to be negative 1 over x. And it's between 0 and 1, but because I can't evaluate it at 1, I have to use a limit for that bound. So negative 1 over 1, that one I can do no problem. And then minus negative, so plus. This is going to become the limit as x approaches 0 of 1 over x. So as I consider that limit, what I consider is that this limit actually is infinite. So this goes to infinity. So essentially what I end up with is negative 1 plus infinity. So obviously this just goes to infinity. So this actually is not a finite area. This improper integral does not have a solution, a numerical solution. It's unlimited. Another situation can occur if the interval itself is unbounded, and this is actually in our particular course what we're going to focus on a little bit more, and that is where my integral involves either one or the other, or possibly both boundaries are negative infinity or infinity. So this particular integral, it really would be extra improper to go negative infinity to infinity because it's not a continuous interval. So that's a whole other ball of wax that we're not going to deal with. But if I go from 1 to infinity in this instance, this then would represent, so if 1 is here, it's still going to represent an unbounded area because it is still technically infinite going off to the left here. And again, I deal with it by using limits. So the antiderivative being negative 1 over x, evaluated from 1 to infinity. On the infinity side, I have to deal with a limit. So this is the limit as x approaches infinity of negative 1 over x minus, so plus 1 over 1. Now, in this case, the limit actually does exist. The limit as x approaches infinity of negative 1 over x is in fact 0. So in this particular instance, the solution to this improper integral is actually just 1. So there is a finite area. So in both cases, if I look at what's happening, it kind of seems like roughly the same thing should be happening, that I have a curve that is approaching an axis or an asymptote, and an area that's being sought for this infinite area as the edge of it approaches the asymptote. But what we can see is that sometimes that area is finite and sometimes it is actually infinite. So how we can tell the difference, we have to look at a limit and see if the limit exists.